This tutorial is an application of solving a system of ordinary differential equations, and this also introduces ODE 45, which is a MATLAB function that can help solve a system of ordinary differential equations. So for this purpose, we'll look at the predator-prey model given in the book on page 815. It's also called Lotka-Volterra equation, and it's a set of equations that basically relates the population of or change of population of a predator and a prey. So in this case, let's say X represented the population of deer and Y represented the population of tigers. And so deers are prey to tigers, and tigers need to eat deer to sustain themselves. So the population dynamics of those two species can be related through this kind of a system of differential equation. So we will implement this system in MATLAB using ODE 45. First of all, let's look at help of ODE 45. What this does is that just like ODE 23 that we have covered before, we need to provide it the function that provides the slope information. We need to provide the span over which we are trying to determine this function and initial condition. And the output is two arrays. The first array is the domain over which the values are found, and then the second provides the values of the function that we were trying to find in this case. So for this model, let's look at the problem that is given in your book. So A, B, C, D for this model are given, and we can again transform this model into a state function. So S is the X and Y population as a vector. Slope function is the right hand side of these equations, and the initial condition in our case is 2 to 1. And we need to run this model from 0 to 30 time units. So in order to implement this, first of all, we define all the parameters of the model, and then we also define the time domain. So in this case, we know our time domain goes from t equal to 0 to t equal and t is equal to tn, which is 30 time units. The initial condition is 2 and 1, so there are two prey members and one predator member in the population. And now we define the ODE system. So ODE system is a function that depends upon time and state, and we know that the first state variable is X and second state variable is Y. So if we are trying to implement this, it's A times first state variable minus B times first and second state variables, and that's what this first part is: A times X minus B times X and Y. Similarly, the second entry of the slope function or ODE system is minus C times second state variable plus D times first and second state variables, and that's what we have done here: minus C times Y plus D times X and Y. So if we define this function, and we know we have done this before in other labs, so this is the we're calling it ODE system. Now the ODE 45, as we learned, uses the ODE system, the span of the information over which we are trying, or the domain over which we are trying to determine the function, and the initial value, which in our case is 2 and 1. So we run this, and it gives us T out, and those are the values going from 0 all the way to 30. And then it also gives us the state values at these time intervals, and as you can see, it provides us two columns. The first one is for X, the second one is for Y. And it gives us that initially there were two prey members and one predator member. And of course, this is a continuous model. So this could be 2,000 or 2 million, but it's progressing. So initially, because there is only one predator, the predator population is reducing, but the prey population is increasing. And let's plot this to see what does it look like. So we can use plot function, and here is another command that you can use to put legend on this plot. So this is basically saying that the first column is prey, the second column is legend, predator, and it will put a little legend at the top. So now you can compare this to the plot in the book, and you will see that the prey and predator populations are off by a certain phase. So when the prey population increases to maximum, that's when the predator also starts to increase, because there is a lot of food to eat, so they keep increasing. But because they are eating all of these preys, there comes a point when prey population will start to reduce, and eventually it will affect the predator population, because then there is not enough food for them to eat, and this kind of cycle of the ecosystem continues. Now this can be further complicated by including, let's say, seasons and grass, but at the end you will see the dynamics of the population in a given ecosystem using this model. So this should give you some intuition about how differential equations are telling us about physical and geophysical world, and how through numerical methods we can actually learn about the dynamics of various important variables of these systems.